Welcome. Good morning. I'm going to be talking about transactions, which may be unusual for Reactive Summit, but we'll see how it goes. This is the rough plan of my talk. We'll start with the basics, talk about challenges, and then I'll talk about what we do in Orleans about distributed transactions and how things work. So the canonical example of transactions we probably all know is if you need to transfer a sum of money, $100, from account A to account B, what do we expect, right? So we don't want money to be on both accounts or in neither account. So we want all or nothing atomicity. We don't want to violate any consistency constraints. So we need consistency, like no zero balance, the negative balance, things like that. We don't want to see intermediate results. We want isolation, so that if the money wasn't actually transferred but already spent for another transaction, that's not allowed. And we want everything to be reliable, durable. So these are asset guarantees, like the standard definition of asset transactions. And for decades, we've got databases taking care of that. So you have Oracles and SQL servers of the world doing this on a single server, which was easier because you run on the box, which you fully control, have access to memory, you don't have network interrupting processing. So it's pretty easy to do compared to a distributed case, and that's why the development for the last 1 or 2 decades has been focused on this trade-off between consistency, isolation levels, and performance. So by reducing consistency guarantees, you can improve throughput. That's been sort of the case of development in database systems. But if we look at distributed transactions, that's a different game altogether. And there the setup is roughly like this. So you have these servers that are called resource managers, and there are standard protocols for that, for example, XOpen. So when the application needs to do distributed transaction, that's how it works. So there's a coordinator. In Microsoft world, there's Microsoft Distributed Transaction Coordinator, MSDTC. So the application code makes a call to the coordinator and obtains a unique transaction ID. And then it starts calling resource managers. They pass in this transaction ID as part of their request. So it calls several resource managers, and when it's done with all it needs to do, it calls transaction coordinator and say, I need to commit this transaction, I'm ready. And this is where transaction coordinator starts two-phase commit protocol. It calls coordinators, resource managers, and say prepare. So they prepare a state in their databases, and then it calls again to say commit. So if everything succeeds, we're done, we're good, transaction succeeded. So this is kind of in theory, and that works. The protocol has been known since early 70s. It's all good. But in practice, life is more challenging than that. So for example, configuration. To make the systems work seamlessly together, you need to configure quite a bit. I took a snapshot from a Microsoft blog post about how to configure Microsoft Windows Server with a firewall to work with Microsoft Distributed Transaction Coordinator to work with SQL Server. So if it takes that kind of blog post to explain how to configure things, life is not easy. So there's protocol, but it's not really 100% compatible. Different vendors implement them differently. So there are compatibility issues. But the biggest complaint about distributed transactions is really performance. Because you have this round trips, message passing, you have transaction coordinator taking logs on the resource managers, it's hard to get high throughput. And this approach has been fine for decades, because if you process tens or maybe hundreds of transactions per second, that's fine. That performance is sufficient. But with the web age, with the internet scale applications, that was not enough anymore, because we're dealing with millions of users, millions of transactions, thousands of transactions per second. And this approach essentially was considered a failure. And the reason for that is really the cap theorem, because you have, who knows what the cap theorem is? I hope everyone does. So with imperfect network, you cannot achieve consistency and availability, and that's the trade-off that you're dealing with here. So distributed transactions were considered dead. Like early 2000, people say, you give up. You will not have distributed transactions anymore. And to me, the manifesto of this statement was this paper that was published, I believe in 2007, by Pat Halland, And it's interesting that Pat is the transactions guy, the database guy. He worked with Jim Gray, he worked in tandem systems. So he would be the one arguing, you would think, for transactions, distributed transactions forever. But he claimed in this paper, and I highlighted that, in this new age of internet scale computing, developers should give up and build systems without distributed transactions. I highlighted in green his speculation, his insight that in the future there might be some other approaches that would be different but would solve the problem in a different way. And those approaches indeed emerged. Like, for example, event sourcing and CQRS, command query responsibility segregation. There are different ways to do it, and we can argue several days about what's the right event sourcing in CQRS, but roughly the idea is that when you do writes, you append events. So instead of only writing the state, you append an event that describes the change, and then these write events, they get processed asynchronously into aggregation into different stores that are used for reads. So you separate your reads and writes. So your writes flow asynchronously into the read store for queries. I took this picture from the white paper that was published by a group at Microsoft, and it's interestingly one of the authors of it worked in my group on Orleans later. So if you look at event sourcing approach in our bank transfer account, bank transfer of an account example, it roughly looks like this. So we receive a request to transfer money. And the first thing we do, we write it as an event, as a fact. After a validation that this is possible, there is no violations in this operation as much as possible, but we write it into a stream of events as a request for transfer. And then we can respond that we succeeded. And asynchronously, this initial event will be transformed into two different events for different accounts, for account A and account B. So for one, it would be withdrawal request, for the other one would be deposit request. And they do the same. They write this request as events in their event streams, event queues. So this is a very powerful approach. It allows you to scale, and it's very good for many, many scenarios. But I would argue that what you get here out of all of ACID, you only get D, durability. You don't have atomicity guarantees because everything is done asynchronously, and you may have some operations succeed, not operation fail for a number of reasons. Consistency is only eventual, and there is no isolation. You can see partial results. I want to stress it's a great pattern. I'm not arguing against it. But what if you need more than that? And again, there are like religious debates about everything should be eventual or not. I'm not going to go down that, but there are facts that people are looking, again, at consistency. There was a paper in 2012 published by Google about Spanner, their distributed, consistent SQL-like database. And if you see in the motivational piece of this paper, they're arguing that their developers have a hard time dealing with eventual consistency in several different application cases. And Google generally doesn't hire the below average engineers. So they're pretty smart engineers, very capable. And so here they are telling us it's very hard to deal with eventual consistency in certain applications. So that's why they built a Spanner. And if you look at the Cloud Spanner, they have this table where they combine these green checkboxes from single machine consistent database and key value stores, NoSQL key value stores, and say we achieved the perfect combination of the green checkboxes. And you'd think it's impossible because of the CAP theorem, because essentially they're claiming they sort of exceeded the speed of light or broke general laws of physics. So Eric Brewer, who is the author of the CAP theorem, he published this paper to explain what they actually mean here. Because he's a scientist, he cannot just argue that we solved the physics problem. He's saying that in Spanner, it's effectively a CA system. So it effectively achieves consistency and availability at the same time. And it is possible only because Google controls their network physically. They have all the fibers, switches, all software and switches and routers. He's saying the probability of network failures in our system is so low that we can claim we're effectively CA. But in fact, he's saying it's a CP system. So if there's any network issue, they will prefer consistency, the system will be unavailable. So that's Google's approach. The alternative approach is the Cosmos DB. It's the Microsoft Azure offering of global scale replicated database. It gives you a choice of the 5 consistency models, from strong consistency to eventual consistency and a few things in between. So it's a different approach for solving the same problem. But I think if we step back from these ways to solve the consistency problem, we see that we're still getting a single database. So you have to buy into either, say, Cloud Spanner or SQL or Cosmos DB, and then if that works for you, that's great. But what if you need to combine 2 systems? In that way, in that sense, it's even worse than distributed transactions before. You cannot really run a transaction across Spanner and Cosmos DB or SQL and Cosmos DB. You have to buy into a single database, and that will work for you, just like a single machine database before. Now it's distributed, but still a single solution. So let's talk a little bit about Orleans. Who has heard about Orleans before? I'm just curious. Oh, good. So some people. Orleans is the framework for building cloud services, which is not actually accurate. It's a framework for building distributed applications and scalable distributed applications. But because cloud is where you benefit the most, we explain as a cloud framework. So it solves 2 problems. It gives it improves programmability of productivity of developers by giving them a programming model that's easy to use and reduces the amount of code they need to write by several factors. And it also makes these applications scalable by default. At the 30,000-foot level, it looks like this. There is a cluster of servers where the actors live. So it's based on the actor model, but it's different from Akka. Who's familiar with Akka here? I assume everyone almost, right? So unlike in Akka, where you explicitly, or in Erlang and other traditional implementation of the actor model, in Orleans, these actors, what we call grains, they live forever. So you never create them, you never delete them. They're like distributed objects, and it's easy to think of them as distributed objects that live on the cluster of servers. So each grain has a stable identity. For example, if you model a user as a grain, you can have an email or phone number or social security number as the key. That's the stable identity. And then by knowing that identity, you can always get the reference to that grain and make a call. And it's the job of the Orleans runtime to create an instance of that object somewhere in the cluster, process your request, hold it in memory while you're using it, and then remove it from memory when it's idle. So by following the actor model, grain encapsulates state of itself. So you cannot directly access state of other grains. It's only message passing between them. So it's really, we call it virtual actor model, and that's kind of what we publish in our paper. So it's the actor model, but these actors are created and managed by the runtime on an as-needed basis. So grain manages its own state, so it can have its own persistence. So you can use different persistence stores for different grains. For example, for your user profile, you can use maybe key value store. For your orders, you may have a table store or a SQL database. So it's really, it decouples you from storage. And if you look at the event sourcing approach, it's very easy to implement because each grain can maintain its own stream of events and apply them. Because there is no single point of coordination in the system, and because these actors can be created on the cluster, on the scalable elastic cluster of servers, it scales really well. So you have very good scalability. But when we talk about consistency, there's really no built-in coordination. There is nothing that the system offers you. So if we go back to ACID, we're really, again, getting just D and none of the other letters. So here's how our canonical example of money transfer looks in Orleans. Your web front-end server receives a request to transfer money, makes a call to a bank grain, say, I need to transfer from A to B. Bank grain calls withdrawal and deposit on account grains, account A and account B. They modify their state, and they write updated state to database. And then once that happens, you have asynchronous acknowledgement, and eventually it all propagates, and we complete the transaction operation. So that's when everything goes wrong. That's the happy path. And if you have any experience in real life, you always focus on unhappy path. What happens? Immediately think, what happens if something goes wrong, right? Because the write may fail, right, to database, or maybe write succeeded, but the acknowledgement was lost because of a network issue or because the machine got rebooted in between or failed. What if messages between grains got lost for the same physical hardware reasons or machine reboot? So everything is really prone to failure here. And because of that, in reality, here's what people are forced to do. And I've seen, this is a simplified version of what I've seen many times implemented in Orleans applications by various users. So when BankGrain receives a request, it needs to record it in its own storage with unique ID so that if something fails and the operation is retried, it will know to deduplicate this operation, say, hey, I already processed this request. It will not try to do it again. Even that is not enough, because what if everything fails? How do I know that the BankGrain needs to process this operation? Well, you need a recovery mechanism. In Orleans, we have this notion of reminders. It's like a persistent timer. So this BankGrain can record, say, invoke me 5 minutes later. If I'm not done, I will rerun the operation. So only after that, we can start calling the count grains, and then they do their work, and hopefully everything goes fine. And then when the responses come back to BankGrain, it needs to record the fact that this operation got processed so that it will not try to retry it again, and needs to remove recovery mechanism and needs to only after that return back. Like I said, this is an oversimplified picture, and reality is much more complex than that, because every count grain also needs to take care of deduplication, possible retries, and all of that complexity, which reminds me of this observation by Martin Kleppmann he made years ago, that in any kind of complex system like this, you see sort of half thought through bug riddle, slow implementation of half transactions. So everyone is trying to do some kind of form of transactions, but even that approach doesn't give you asset, really. It only takes care of reliability of execution, maybe eventual consistency. So I would argue that what we want what we used to have in say MTS Comp Plus days, where you just put an attribute on the operation. You say, transfer operation is transactional. It requires a new transaction. Whenever BankGrain is called to transfer money, that starts a new transaction. And then deposit and withdrawal operation are also transactional. They can be used as part of transaction, but they cannot be just called arbitrarily. And so when everything happens fine, transaction executes and completes, we're good. So what we really want, I would argue, we want asset guarantees. So if, say, we started with $500 on both accounts, and we do this process operation, what we want to achieve, arrive to the new state of 400 and 600. And if anything goes through, like we want this operation to be atomic, if anything goes through, we just return back to 500 state on both accounts as if nothing happened. I would argue that's what we want as developers, the system to just work and take care of that and not build this complex machinery to half achieve the same result. That's really what Orleans transactions are about. If we look at the programming model of it, so this is how we define transfer operation on the BankGrain interface. I took it straight from a sample that we have there on GitHub. So you put the transactional attribute on the method, and the method takes 2 IDs of accounts and the amount you want to transfer. Similarly, on the account grain, you have 3 operations: withdraw, deposit, and get balance. And withdraw and deposit, they require the join existing transaction. Less obvious is why get balance needs a transactional attribute. But if we think about isolation, we don't want get balance to return some intermediate result. We want to make sure when get balance returns, it returns a committed state that can be relied on. So that's why it has create or joined attribute on it. And implementation of the transfer operation on the BankGrain is really like this 5 lines of code. So we get references to account grains. We make calls to withdraw and deposit, and those calls being asynchronous return the task. Who knows what a task is in .NET? It's a promise. It's like asynchronous future. So it's something that will finish complete in the future, but doesn't block thread. So I can get these two promises, T1 and T2. I can join them when all operation and return another promise that will be resolved when both operations complete successfully, or will be broken with an exception if one of them fails. So that's really the code that I need to write in the bank transfer method. Now, on the count grain side, so we defined state of this grain. In this simple sample, state has only one integer value of the balance of the count, but you can have a complex data structure there as well, many properties. And that a form of this balance gets injected through dependency injection in the constructor of the count grain. There is an attribute there to wire it at the configuration time to a persistent store that you want and things like that to configure it. But in essence, you get this balance object back through DI. And when we look at how operations are implemented, deposit and withdrawal, you just pass lambdas, and this lambdas, the only difference is plus or minus in this increment decrement operation. And we need this as lambda because they can be invoked on a different thread later. And for read, so we just, for get balance, we return the value. That's it. That's really all the code, the application code you write for this kind of simple operation. You need some configuration. When you configure the server, we call silo. Silo is where the grains live. So you need to say, I want to use transactions. So in the build pattern, you add transactions and you add providers, storage providers. In sample, it's in-memory storage. Just you can run on a single machine. And that's how the system is configured. So that's the programmability experience. And of course, you're interested what's under the hood. There's two gentlemen, Phil Bernstein and Tamer Eldib. They work on this transaction system for a couple of years. And that's the Phil Bernstein of transaction processing, who was, I think most colleges use his book to teach transactions these days. So they published this paper a couple of years ago about transactions. And I'm not joking, this is the architectural diagram from the paper. There is no other architectural diagram there. So I thought I'd better zoom in and show more details. So here's the cluster of Orleans servers. We call them silos, as I mentioned. They can use different storages, blue and green, for different grain classes, grain types. For transactions, we had the notion of transaction manager. So it's a separate server that runs on the side and uses its own storage for storing transactions log. That's why this brown storage is for transactions manager. Inside each silo, we instantiate and run at any point in time. It can be like hundreds of thousands or millions of grains, depending on the complexity and how expensive operations are. And they all communicate with transaction manager via transaction agent that can act as a messenger on behalf of all grains in the silo because you don't want them individually talking to the manager. Transaction manager is a single point of contention and failure here. And for reliability, fault tolerance, you probably want to run a backup, a standby that can take over in case the transaction manager fails. So it can detect that the main one failed, load a transaction log from storage, and continue running. So here's how two-phase commit is done in the system. So our bank grain receives a request to transfer. And the silo, the server where the bank grain runs, it becomes transaction coordinator for this transaction. So it calls grain A first to withdraw the money. What that does, it puts a lock on grain A, performs the operation, and returns the acknowledgement back. In parallel, we call, when it returns back, it not only returns that it succeeded, but also returns a list of dependent transactions, its dependencies. So if this is transaction A, in my example, it returns that grain A depends on previous transaction n minus 5. So it's important because this is a dependency chain in transaction execution. Then we call grain B to deposit, and the same thing happens. So the grain gets locked, and when a call returns, it returns dependencies. In this case, dependency in n minus 2. So now we're ready to complete this operation. So what transaction coordinator does, it calls prepare, a standard call in two-phase commit, and as part of prepare, both grains that write their prepare records into storage, so they can be committed. And when prepare is done, the lock is removed. So it's the early lock release technique, which improves throughput by allowing to keep a lock for a very short period of time so that grains get unlocked very fast. So likewise, grain B gets unlocked, and now we're ready to commit. And before we can commit transaction, we need to talk to transaction manager. And that's the single thing that transaction manager does, apart from allocating transaction IDs. So transaction coordinator calls transaction manager and say, I have this transaction and that are ready to commit. It has grain A and grain B participate in it. And it depends on n-5 and n-2 on two previous transactions. So if those transactions haven't committed yet, transaction manager will have to wait for n-5 and n-2 to commit. And if they committed successfully, it writes the commit record to its storage and returns committed. Now we're all good. We can return success. If there's any failure in the process, then this validation transaction will simply return the board. So we wait for dependency and say dependent transaction failed. So it returns the board. This transaction cannot be committed, and everything gets unwound as if, again, transaction didn't happen. So what I would say are highlights of this approach. As you can see, we give asset guarantees, asset transactions across non-transactional stores. So these grains, they can use different storage techniques. They can be used blob store or key value store or maybe table store, anything. Storage technologies that do not support transactions by themselves, but we can have asset transactions on top of them. I would argue that this approach scales to pretty high rates for applications that allow for that. So of course, if you have a single point of contention, if every account grain needs to talk to some I don't know, authority grain, that will not scale. But so long as you have enough of these pairs, groups of grains that can independently execute transactions that don't impact other groups of grains, you can scale really well. And that's good for internet scale scenarios. Like for example, in gaming, you want to do in-game commerce, you want to transfer items between different accounts, different players. You can do that because transfers between players are independent from transfer of other players, and you may have millions of them. I hope I convinced you that the programming model is pretty straightforward and intuitive. And because of this combination, this approach, I would argue, works for a wide range of applications. Not for all applications, but for a wide range of applications. Of course, the approach has drawbacks. So I mentioned this dependency chain where transaction and dependent on previous transactions. That may cause cascading aborts. So if you have a long chain of dependencies in one transaction in the beginning, if it aborts the whole chain of transactions. In the paper, Phil and Tamer, they prove that it's only possible when there's physical failure, when the server crashes or something like that happens. So it should be pretty rare, but it is possible. Maybe a less obvious drawback is that, remember that getBalance method, they had transactional attribute. Because of that, even when you do read-only operation like getBalance, it has to go and do round trip with transaction manager. It has to validate its transaction, even though it's just a read operation. So it adds to latency, but doesn't impact throughput, really. The biggest complaint I've heard is that is a standalone TM. It's an extra operational cost. So you have to deploy this single thing. You have to take care of its reliability, fault tolerance. I was surprised to hear that even more than the fact that centralized TM is a single point of failure and scalability bottleneck. Scalability is an interesting question because, I mean, there are different applications, different businesses, and like in the paper, Phil and Tamer, they showed that they tested transaction manager on an 8-core VM that can handle roughly 150,000 transactions per second. And I would argue if your business handles 150,000 financial operations, money transfer, you have a good problem. It's a good problem to have if that's not enough. So in my experience, people first mostly complain about the operational part of it, that you have to manage this, you have to configure. How they achieve this high throughput, there are some simple tricks. I mean, simple conceptually, but there's implementation is not necessarily simple. Like batching is decades-old technique. So instead of sending validation requests for a single transaction to a transaction manager, you can send requests, say, accumulate for 50 millisecond transaction on each of the transaction coordinators, send them as a batch, and then receive batch results back. So for example, some transactions committed and some aborted. By doing a single round trip for a batch of operations, we're increased throughput, of course, of the server. So this was implemented in a ship as a beta version of Orleans transactions back in March when we released a big Orleans release 2.0, where the biggest goal was to make Orleans cross-platform to run on Linux, not just on Windows, but on Linux, Mac OS. So we shipped transactions as a beta form, say this is what it is. And we continued working on it after that. Orleans itself originated in Microsoft Research back years ago, and then it got transferred into Proto Group with the team. But we continued working with research since then. And last summer, we had Chris and Alejandro as PhD interns, mentored by Phil and Sebastian in MSR, and they work on the new protocol that would improve what I just showed you, the original implementation. So we call it Transaction Manager v2. So if you look at the picture that I just showed you, where this standalone transaction manager that validates transactions, the idea is, again, simple in the hindsight, not necessarily a trivial implementation. Instead of doing that, we make the grain itself a transaction manager. So any grain that originates in transaction, in our example, bank grain, it becomes a transaction manager for this transaction. All it needs to do, it needs to add additional storage or part of the storage already uses maybe for a commit record so that you can record a committed transaction. Everything else stays the same. You get probably lower raw performance here because you don't have this benefit of batching by sending large batches of requests to a single server, but you have ideal scalability because now there is no single bottleneck in the system. And you can, by elastically expanding the cluster, you can achieve higher throughput than the previous design. You also don't have a single point of failure. You don't have to deploy the server. It's just part of the whole Orleans runtime that you deploy anyway for your application. So if you look at the drawbacks of the original design that I mentioned, single grain transaction, the read operations, they don't need to do any round trip anymore because they arrive with transaction manager, which is the grain itself, and that problem is solved. There is no extra round trip. Obviously, there is no standalone TM anymore, and the bottleneck is gone. The cascading aborts are still possible. That didn't change, but as I mentioned, they should only happen when you have a physical failure of the server or hardware. And best of all, it's all open source. It's not some proprietary technology. This is screenshots of the Orleans repository, and in the middle, the screenshot in the middle, that's the pull request by Sebastian for initial pull request for V2 of Transaction Manager. And the third screenshot is somebody in the community, this person, I think John Steinage, implemented a provider, because the Orleans has provider model, they can integrate with anything, implemented a transactional storage provider for AWS DynamoDB. Just contribution from the community. So open source is great, and my team has been working open source kind of years before it was officially claimed new Microsoft, like the open way of building software, and we've been enjoying ever since. Because it's very good to work with a community of people around the world that just passionate about technology, want to collaborate and contribute and work with you. For conclusion, I want to give you a few things. So to my surprise, and maybe just me, but to my surprise, there's still a lot of space for innovation in this whole space of transaction and databases. Because when Phil first started saying, Phil Bernstein saying, well, we need to add transactions to our liens. My gut reaction, initial intuition was why? The transactions is a solved problem and they don't scale. Why would we add transactions to something scalable like virtual actor model framework? But of course, this development proved me wrong, so I changed my opinion once I kind of worked with the research team and understood what they were trying to do. And especially when talk to our users, like for example, our sister team runs a virtual commerce service for games. So they came to us and say, we need this, this, and this, and all of them included transactional functionality. Because otherwise, they would have to run a very complex code, and the code is complex is obviously difficult to maintain. So they want transaction, and we work with them, and they're happy about it. So this is my learning that the space is still wide open, and there's still a lot of happening in it. If you look at CockroachDB, FoundationDB, OrangoDB, there's a lot of innovation that is still happening in this space that similarly has been solved back in the 70s. This is probably the main point I want to make, is that I would argue that in early 2000s, when the web scale started, we sort of threw away all the knowledge almost of previous decades, and we switched to the stateless model, where we build systems where there's stateless front end, stateless middle tier, and some storage behind. And I would argue because of that, we threw the baby with the bathwater. So essentially, we degenerated the middle tier into a very simplistic layer. And actually, there's the layer where we can do a lot more. So in our liens, we use it, we build middle tier with our liens, which is a stateful system. It allows us to build things like transactions, and there's more work that is happening there. Like Phil Bernstein is working on edit indexing and querying, and has this vision paper of building what he calls actor-oriented databases, so sort of new incarnation of object databases from the past. And middle tier is very powerful because it allows you to decouple yourself, decouple your logic, and build a lot of more functionality that is not tied necessarily to storage. Otherwise, you have to put all this functionality in terms of store procs and all of that and be constrained by what storage gives you. And I mentioned open source. It's really, I think, should be the default. Even still today, we need to receive permission to open source. In my opinion, it should be the other way around. You should receive permission not to open source something. You may have some secret sauce that you don't want to share. But what I've seen, that usually is a small percentage of your whole code base, and everyone benefits from most of the code being in the open source. And that's why I invite everyone to look at our code and participate and critique and submit your issues and your pull requests. And I think I still have a few minutes, right? I wanted to, speaking of open source, talk about this individual. So Dimitri joined our community literally like 3 years ago, and he started contributing pull requests focusing on performance. So it could be like 5% improvement, 10%, 15%, 20%. At some point, a member of my team, Xiaozhen, she presented internally, she gave an internal talk about the benefits of open source. So what she did, she plotted our nightly throughput measurements, performance test of our liens over time, and correlated with pull requests from Dimitri, saying, look, here's where we had jumps in throughput. And at the time we calculated, he nearly doubled our throughput. I think by now it's almost like 3x. So 2.6 is a conservative estimate. And so the members of my team, they were telling me, we should hire this guy. You should hire this guy. And I don't have headcount. I can't. So I had to wait. Last contribution he made recently was he completely rewrote the scheduler. And that's the hardware system that's responsible for making everything the guaranteed single-threaded execution, reentrancy. Part of the core team, we were afraid to touch this piece of code. It's so fragile, so core. And he submits a pull request that makes it 30% faster, much easier to debug because of it uses the TPL in a different way. So we'll look at it. We're scared to ship it as part of 2.0, but our last released 2.1 a few weeks ago. That was the biggest change there, new scheduler, it improved throughput by 30%. So eventually I got headcount. And I need to convince the management because he was in Ukraine. And if you're familiar with H-1B process, that's really a horrible process. You have a lottery. So I had to convince management that it's worth it to take this risk and apply for visa and wait for like 4, 5, 6 months, hoping that win the lottery, which we did. Won the lottery and get the visa. And then there was a hiccup with startup process. So eventually, his start date was set for October 15th, last Monday. And a couple days later, I learned that Dimitri passed away 3 days before starting. So I apologize for sharing this, but I felt like I had to do it because he was such a member of a community. He was really loved by the team, everybody. So it's a huge loss for us. He was really had to start a team and had the whole future ahead of him. Kind of his career would jump. So it was a big loss. Thank you. And I think I still have time for questions. Yes, Steve? Good. Oh, we have a mic, I think, right? Oh, yeah. Please come to the mic because you need to record it.
Hi, Sergey. How different is this from the database Saga approach?
How different it is from Sagas?
Yeah.
So Sagas, they don't give you atomicity or isolation, right? Sagas is just a way to, essentially it's a workflow that you can compensate for any kind of failures later. So you can see intermediate results, like in the classical example of booking of hotel and flights. You may have the whole thing canceled, but in the meantime see that the hotel is booked or car. With ACID, you will see all of them succeed or not. That's atomicity. And isolation will not let you see intermediate results. That's a big difference. Can you come to the mic, please?
So in the screenshot where you're showing the transaction manager, right, and he coordinates with the grain A and grain B, right, and they write the storage and they do the prepare as part of the two-phase commit. At some point, if there's an abort operation, the grain A and grain B, they have to undo or do something back to the storage that they're writing to, right? You're not showing the details of that piece there. Mm-hmm. Curious, is there a paper or something that goes into the details of what's going on there?
Yeah, so I think Phil is working on a new version of the paper, but also there is code, so you can just see what happens. So roughly, because there is runtime, so it's not, Grain doesn't need to write code for that. So Grain tries to submit like updates, and there is transactional logic that sees that there is prepare, and if there is prepare record found, but there is no commit, it tries to validate if that transaction was committed or aborted. So the runtime will talk to transaction manager and ask, what happened to this transaction? Has it been committed or not? And eventually, it should get either committed or aborted. There is no other option.
So if I wanted to write a persistent store, my guess is that you can plug in any kind of persistent store at any of these layers, right? So if I wanted to come in and plug in my own persistent store that writes to some proprietary store or whatever and wants to support this transaction, I would have to implement something that kind of touches and writes these markers for the prepare and commit on that level.
Your provider will need to persist metadata, not just state, but also metadata given to you. So you don't have to necessarily interpret what the metadata is, just need to persist it.
Okay.
Trying to make sure that I understood what you just said. Mm-hmm. If I understand well, the local record is in kind of provisional storage until it gets a commit acknowledged. Is that right?
So local state is in memory. So when there is a prepare call, then it gets written to persistent storage.
But it's too early. We don't know that it's a commit yet.
It's a provisional, like you said.
So it's a separate queue, so to speak.
It's a separate record with metadata saying that this is prepare record. Okay. Like it hasn't been committed.
Excellent. Thanks.
Thank you.